Hello, I'm Cyrus Hettle, and I'll be speaking about balanced districting on grid graphs with provable compactness and contiguity. This is based on joint work with Swati Gupta, Yao Xia, and Shixiang. So, as an overview, I'll introduce districting problems, talk about various considerations and objectives and related work, and what our algorithmic goals are. Then I'll discuss the various techniques that we use in some different settings for districting, and finally some computational results evaluating our method on both some synthetic and real-world instances. So districting problems are among the most well-studied and oldest and most well-studied in both theoretical computer science and operations research. And at its simplest level, we're given a map composed of many small regions, and we want to partition these regions into a given number of parts with some additional desired properties. And there are many applications, civic applications in district and workload balance for schools and police, among other things, political districting and studying gerrymandering, and even in parallel computing. And across all these many applications, there's three objectives that are particularly common and that we would like to study. First, there's balance. A district should be approximately equally sized or have equal population or equal workload. They should be contiguous, one connected piece, and they should be compact. And there's many metrics for this, but we'll focus on low perimeter or a low number of cut edges. And as we'll see, there's many approximation algorithms and heuristics for these, but obtaining guarantees for all three objectives simultaneously and efficiently is a difficult problem. So here's our problem statement. As input, we are given a graph on vertex set V with edge set E. We have non-negative weights on the vertices. We have some desired number of parts K, and we have some non-negative balance parameter epsilon. And our goal is to partition the vertex set into exactly K parts, such that each subgraph, the subgraph induced by each part is connected, contiguity, and the total weight of each part is within epsilon fraction of the average part weight A. So this is the epsilon balance condition. And finally, our objective is compactness. We want to minimize the number of cut edges. So here's an overview of some related work, both some polynomial time approximation algorithms and some heuristic methods. So we can see in the polynomial time approximation algorithms, these apply in various settings, some more general, just general polynomial weighted graphs, some just on grid graphs, or other kinds of mesh. There's various tolerances for balance. Some are parameterized. You can choose any epsilon you want. Others just give a 2 approximation or require epsilon equals 0. There's various compactness guarantees, sort of scaling with how general the setting is. But common to all of these, there's no contiguity guarantee. And on the other side, with the heuristic methods, so methods such as IP or k-means, local search, these apply to more general settings, and they guarantee contiguity, which is great. But balance is not always guaranteed. Compactness often performs well, but there's no theoretical guarantees. And often, for instance, for the IPs, performance is not great. IPs, even on medium-sized cases, often don't converge very well. So with the goal of trying to achieve all these objectives and do it efficiently, we're going to focus on the setting where the graph is a square hexagonal grid graph. And this is possible in many applications. So for instance, if we have a map, we can superimpose a square or hexagonal mesh onto the region and get a square hexagonal grid graph from that, and then solve the partitioning problem on that graph and apply it to the map. And we're also going to look at three kinds of vertex weights. So unweighted vertices that just have constant weight, weighted vertices where the weight varies from vertex to vertex, and finally we'll also consider stochastic weights, where each vertex has its own independent random distribution xv, and after we fix a partition, each vertex's weight is drawn at random from its distribution. So let's look now at our techniques for these various settings and the guarantees that we get. So let's start with the simplest case, the unweighted case. And let's talk about the striping technique, which was introduced by Christo and Meyer. So in an unweighted square grid graph with epsilon equals 0, so perfect balance, every part has the exact same number of vertices, The minimum perimeter parts are square or almost square, and they have perimeter 2 times the ceiling of 2 times square root of A. Remember, A is our average part size. And so here's an example. This is a 4 by 15 rectangle. You can imagine maybe this is one part of a larger graph. And in the striping technique, we proceed down the columns and from left to right across the graph. And we're going to continue doing this until we accumulate A vertices. So for instance, here we go down the first row, down the first column, we get 4 vertices. Down the second row, we have 4 more. Down the third row, we now have 12 vertices. Then we take vertices 13, 14, and 15 from the fourth row. So that's 15, that's our A. We stop, and that's our first part. We continue on to the second part. We take the last vertex in the fourth column, then 12 more from the next 3 columns, 2 more in the 7th column. Now we're up to 15. Again, we cut off. That's our part. And we continue on, we get 2 more parts this way. And as you can see, these parts are indeed square or approximately square, and they're pretty close to getting that ideal minimum perimeter. And so this is the value of the striping technique in producing compact looking and mostly contiguous parts. So inspired by this approach, we give a new algorithm which we call phi-cautious striping, which extends to positive epsilon, so slightly unbalanced, and it guarantees contiguity, in where Christo-Meyer's algorithm did not guarantee contiguity. And we do so by partially striping across strips in the graph, but leaving one region at the end, so the outlined in red here, unpartitioned, and then later partitioning that, proceeding top down instead of left to right, with a few other small modifications. So indeed, this gives a balanced partition, and it's contiguous, and it has a good compactness guarantee, so it's a constant factor approximation, and asymptotically, as the size of the graph grows, the number of cut edges produced by phi-cautious striping will approach the optimum that we can get. And in the special case where epsilon is equal to 0, which Christo and Meyer studied, we get a 1.69 approximation, and we improve their relative error bound by a factor of more than 6, while strengthening their contiguity guarantee. So that's the unweighted case, but how about the weighted case? So again, we're going to be adapting the striping idea, and we give a dynamic programming-based algorithm that we can apply to any weighted Hamiltonian graph. So as additional input to the algorithm, we give it some path P, which we think of as an ordering of the vertices of the graph. And when we're dealing with a square or hexagonal grid graph, we can use the striping idea to create paths. We can see, like you can see here, and after we get to the end of the graph, we turn and snake and proceed to stripe back the other way. And this gives us paths that work quite well in practice. And this also comes with some guarantees. So the cut function is submodular, so straightforward dynamic programming recursions don't quite work. So instead, to make our dynamic programming recursion feasible, we look at cut sizes in subgraphs of our graph that are induced by the first S elements of the path, and then scale this up as S increases. So our guarantee is over all graphs, not just grid graphs. So given a path, our dynamic partitioning algorithm has polynomial running time, and it gives contiguous balanced partition that has minimum cut size over all partitions whose parts are consecutive subpaths of P. So this guarantee does depend on P, but if P is well chosen, the performance here will be quite strong. And in most applications, the running time is very fast. It's order n squared. So it's possible even to generate multiple paths and quickly run this algorithm over each path and choose the best result. So that's the weighted case. Let's move on to the stochastic case now. So for this, we adapt the methods of Kleinberg et al. For online stochastic load balancing. We give an algorithm stochastic load balance partitioning for this case. So the idea of these online load balancing algorithm is we take our random variables xv and we break them into an exceptional part when they are greater than 1 and an unexceptional part when they are at most 1. So the unexceptional and exceptional part sums to our variable. And we check both all the exceptional parts together and all the unexceptional parts together. And if one of these groups is relatively large in some sense, we have all of the xv and recompute the exceptional and unexceptional parts and check again. And we'll repeat this process until both the exceptional parts and unexceptional parts are relatively small. And after we do this I times, we get some new modified vertex weights. And so this is a sort of a moment expression looking at the number of parts k raised to the power of the unexceptional part. So these give us a single value for each vertex, and we input these values into the dynamic program, into the dynamic partitioning algorithm for districting. So this also comes with guarantees. So the stochastic load balancing partitioning algorithm will return a partition whose expected maximum part size is within a constant multiplicative factor of the optimum over all partitions of the vertex set into k parts. And the compactness and contiguity guarantees that we get are inherited from the dynamic partitioning algorithm as well. So this is the similar guarantee to what Kleinberg et al. Obtained in the load balancing setting, but we need some additional considerations that, from the dynamic partitioning algorithm to get these specific balancing guarantees. Finally, we also have guarantees on the variance of the expected part sizes. So if our random distributions are relatively nice, so their variances aren't too big, there's some, at most, some constant multiple of the mean of those distributions, then any partition that's epsilon balanced with respect to its expected part sizes also has a good bound on its expected variance of part sizes. So these are all our combinatorial methods, and we complement them with some simulated annealing approaches, which can make some local search improvements once we've generated our partitions. So how these simulated annealing approaches work is we have a partition and we look at small neighborhoods around it. So for instance, here we have an orange and a blue part, and we consider a set of candidate partitions generated by this where we can make a small number of swaps along the border. So this preserves contiguity, generally doesn't hurt compactness too much, particularly if we use hexagonal grids as opposed to square grids. And then using simulated annealing approaches, we can look at these candidate sets and try to improve balance or compactness or both. So there's an overview of our methods, and let's look now at some experimental results. So first, we have some synthetic instances. So here's a 100 by 100 hexagonal grid that we want to partition into 100 parts. So this has a smoothly varying set of weights, which is in the heat map on the right. So this will force some parts to be much larger than others to achieve the balance that we want. So here our epsilon is 0.05. Each part needs to be within 5% of the average total weight. And using the dynamic partitioning method with a striping path, we can generate a partition on this relatively quite large instance in a reasonable amount of time. So in under an hour, its number of cut edges is within 0.5% of the very compact but also unbalanced partition that we'd get by just taking 10 by 10 squares and filling it up that way. And we can also apply simulated annealing to this and find some local improvements to reduce the cut size, increase compactness even more. So the swaps made by simulated annealing are circled in red on the middle image there. And finally, let's look at some applications to civic districting. So in South Fulton City, Georgia, shown on the left here, so this is a highly non-convex region. We discretize it by covering the city with a hexagonal mesh. This generates a grid graph with about 1,200 vertices. And the workloads of these vertices are based on past 911 call history, both the number of calls and the time taken to resolve them. So first, let's look at districting for the fire department using striping and annealing. So we want to divide South Fulton City into 10 parts. And we can do so with the striping partitioning method with some additional simulated annealing. And indeed, compared to existing plans and methods derived using k-means, our methods significantly reduce the maximum deviation from the mean. So this is increasing balance, and this is reducing the workload in the largest part. So workload is much more spread out, and so we're aiming to reduce waiting time when there's a large number of 911 calls coming in at once. We want that to be spread out. And furthermore, we maintain contiguity and have a very competitive number of cut edges. And that compactness is important because we want each region to be easy to get around in so that response times are fast. Finally, we evaluate the performance of our stochastic methods by drawing police beats with some incomplete information. So here we're going to compare our stochastic method, which uses the knowledge of the entire distribution xv for each vertex, with deterministic methods, where we just look at the mean of the xv and apply partitioning just using those. And we're going to compare these based on their expected part sizes. And furthermore, we're also going to compare partitions based on knowledge of the true distribution with knowledge of only an empirical distribution, where we draw a few samples from the true distribution and just work with those empirical distributions. And this models a lot of uncertainty that we'd have in real-world instances, where we have a limited number of samples, a limited number of 911 calls, and response times for each individual atom in our graph, since we're looking at a fairly fine grid mesh. So this gives us 4 different partitions to look at. And so we generate 100 sets of random distributions, so 100 sets of XV based on the 911 call. We generate these 4 different types of partitions using both the true underlying distributions and increasing sample sizes. And so evaluated by the maximum percent deviation from the average. So we want this to be smaller for better balance. We can see that the stochastic methods in green and blue outperformed the deterministic methods in black and red that just look at the average and disregard the variance in the rest of the structure in these random distributions. And indeed, for larger sample sizes, so once there's at least 8 samples in the true distribution for each vertex, the empirical stochastic method actually outperforms the deterministic method that has knowledge of all the true underlying random variables. And so the stochastic method does indeed produce better expected balance than just looking at the expected sample mean for each vertex. So here are some references, both on other partitioning methods and other related work. Thank you very much.